I'm technical interaction and technical development structure. So I'm talking about something from universal program. I'm in the level of high competition and then universal knowledge. I'm coordination analysis of services signal. So today I am going to introduce the basics of specific information. For example, I'm going to explain what we can now from the significant analysis to explain the amount of problems for those. So yesterday, we had a nice overview of our species types. Well, once the species starts identifying this kind of species symbol, then the most important part is to implement the system that finds out the initiative planning of units and the knowledge of the student. So here is a main here shows the heritability of activities, the quantity itself of those numbers. And the light here shows the monthly local item object. This may be from the volume given. So here, the component analysis shows the mass of a given object, which is denoted by M1, and the y-axis shows the mass of a item, denoted by M2. So by definition, M1 is relevant, so we only need to consider this lower engine is fine. And in current definition, what we compute is the probability-based function over the self-time test. So these high intensity expressive value of the probability function and high intensity means larger level of probability density. We also compute the so-called derivative regions. That is the measure from the total probability value in the certain level. Two controllers given the 50,000 and 90,000 critical region, where the two mass values are relevant to the other. And our class definition is to this kind of possibly probability to function for the level of time that we are using. I'm going to explain how to do it. But before moving on to the results, I'm looking back into what kind of given measure for the revision improvement. So the first kind are the monthly expression objects. So to move to explain this, how we can get a masses from gravitational vector. So I show two simulated position signals. From binary with different mass values. For the hallucinated signal, is the signal from binary is certain bidirectional mass and verified solar mass, and the hallucinated signal is from binary with smaller values, smaller mass values. So the two simulated signals are calculated from a certain frequency of 10 millions. Mostly, we are not intention over time that's and as you can see, higher mass values, meaning that they are sigma shorter. So, because that for higher mass values, by evolution, so by measuring that, obviously, by measuring the similar radiation, we can measure the mass values. And also some in between higher mass values, knowing that we need to still now louder. Similar until also regarding our video sample process.
We cannot separately, measure the masses from the signal amplitude. So masses are basically determined by the signal duration. And in general relativity, it can be shown that the signal frequency evolution is predominantly determined by this special mass combination, which is often called Chirp mass. So typically, this Chirp mass parameter is one of the most precisely measured parameter in CPC parameter estimation. I think the screen is turning off. I don't know. Okay. Okay. In addition to those mass values, signal morphology is also affected by the spin angular momentum of colliding objects through the general relativistic effects. The dominant spin effects come from the spin components in parallel with the orbital angular momentum. So in this movie is going to show a binary evolution with 3 different spin configurations. So the left movie shows the binary evolution for spins aligned, 2 spins aligned with the orbital angular momentum. The middle movie shows that for vanishing spins, and the right figure shows the spins anti-aligned with the orbital angular momentum. And what we will find in this movie is that aligned spins slow down the binary evolution while the anti-aligned spins accelerate it. So let's start. So as you can see, the light binary evolves quicker, and yeah, that this is the first one to merge, and then the middle one is the next one to merge, and then last one, the left one binary is the last one to merge. So reflecting this, the signal duration gets longer for aligned spins. So signal duration is also affected by the parallel spin components. So because signal duration is affected by both masses and the parallel spin components, those values are completely degenerate. If you only look at the signal duration, in reality, we can measure the entire frequency evolution in the detector's frequency band, and the effects of masses and spins have different frequency dependencies. So the degeneracy is to some extent broken, and we can get some information about the parallel spin components. In addition to the parallel spin components, we can also measure the spin components orthogonal to the orbital angular momentum. So this video is going to show the binary evolution with non-vanishing orthogonal spin components. So let's start. Yes. So what happens is that these orthogonal spin components causes the orbital plane to precesses through the general relativity effect. So you can see that the orbital angular momentum is slowly rotating in this movie. Reflecting this precession motion, as you can see in the lower panel, the amplitude and phase of gravitational waveform slowly modulates. So looking at this amplitude and phase modulation, we can get information about the orthogonal spin components. So in summary, by observing the morphology of the signal, we can get information about the masses and spins of colliding objects. Because these masses and spins have imprints from how the binary formed in the past. So by looking at, by measuring those parameter values of a lot of detected CBC signals, we can investigate the formation history of merging compact binaries, and we will hear more. I think we will hear more about this in the next CBC science talk. In addition to masses and spins, if the binary contains a neutron star, then the signal morphology is also affected by the so-called tidal deformability parameter denoted by lambda of a neutron star. So what happens is that, so if the binary contains a neutron star, then this neutron star is tidally deformed by the companion. And this tidal deformation accelerates the binary evolution at the final stage of the inspiral. And it makes the signal slightly shorter, as you can see in the light figure. So measuring this, you can measure the tidal deformability. Because this tidal because the significance of this effect is characterized by the so-called tidal deformability parameter lambda of a neutron star, we can measure this tidal deformability parameter. Because and this tidal deformability parameter lambda depends on the equation of state of highly dense matter inside the neutron star, which is still uncertain. So by measuring this tidal deformability parameter very precisely, we can also constrain the nuclear equation of state and learn the properties of highly dense matter inside the neutron star. Okay, so far I have focused on parameters characterizing the properties of colliding objects. And in addition to those parameters, source direction is also important parameter, and it is crucial information for especially for follow-up electromagnetic observations. And we can measure this source direction by utilizing the data from multiple detectors. So the idea is that because gravitational waves propagate with a finite speed, so they hit multiple detectors with at different arrival time values, as you can see in the light figure. So by observing these different arrival time values at different detectors, we can constrain the source direction. You can also see that the observed signal amplitudes are different among different detectors because that each different detectors have different orientations. So we can also use those amplitude information to improve the source localization. So in summary, to summarize, I list all the parameters characterizing the CBC phenomena in this slide. So we have mass parameters, spin parameters, tidal deformability parameters, source direction parameterized by light ascension declination. And in addition to those parameters, we have a coalescence parameter, distance to the source, and some angle parameters that characterizes the that determines the geometrical configuration of the binary. So in total, we have 15 parameters for binary black hole mergers and one additional tidal parameter per neutron star. So we have many parameters. So this is a bit technical, but I would like to also mention that in real parameter estimation analysis, in collaboration analysis, we use slightly different parameterizations for masses and spins and light ascension declination and coalescence time to improve the efficiency of the analysis. And they are explained in brackets in this slide, these brackets in the slide. Okay. So that's all for the physical parameters. But in addition to those parameters, in collaboration analysis, we also consider additional sets of parameters that that quantifies the uncertainties in detector calibration. So the detector calibration is a process of converting interferometer outputs into gravitational wave strain. And it is known that there are small uncertainties in the detection calibration step. So the right figure shows the estimated uncertainties in calibration uncertainties in amplitude and phase of the LIGO Hanford detector during O3. And you can see that we have amplitude errors of order of 1% and the phase errors of order of 1 degree. So the actual observed, like a reconstructed gravitational wave strain can be modeled by the true gravitational strain multiplied by the 1 plus amplitude error times the phase error factor. And in order to mitigate biases from these uncertainties, we introduce additional parameters that are basically the amplitude errors and phase errors at certain frequency points. And those entire amplitude and phase errors are modeled as spline interpolation of those values. So in summary, we have more parameters. We have more parameters than those than the physical 15 parameters. Okay, that's all about the parameters we consider. And in next, I will explain how to compute the probability density function of those parameters. So to do that, we typically use a Bayesian framework and compute this Bayesian posterior probability distribution, which is a probability of obtaining some certain source parameter values, which is denoted by theta, condition on observed data denoted by D, and the condition on certain signal hypothesis denoted by M. And according to the Bayes theorem, this probability Bayesian posterior distribution can be calculated, but as the likelihood, that is a probability of obtaining data conditioned on theta and signal hypothesis, multiplied by the prior distribution function defined as this, and divided by the evidence factor defined by this expression. So typically, we use L, calligraphic L for likelihood, pi for prior, and Z for evidence. So here I'm just to switch to this standard notation and explain how each of these parts can be obtained. So first, I will explain how to calculate this prior part. So prior distribution is determined to encode our prior knowledge or belief on theta. For example, if we don't have any information about theta, then we use an uninformative prior for pi. For example, if we don't have any information about light acceleration declination, then we use an isotropic prior on light acceleration declination. Or if we don't have any information about the masses, then we can use the uniform prior for mass. On the other hand, if we have some information about the previous observations or theoretical consideration, then we can include those information to prior. For example, if we know the true location from the electromagnetic observation, then we can use the delta function prior centered on the light acceleration declination values reported by this observation. Or if we know mass distribution from previous observation, then we can use that for mass prior. And how about evidence? So evidence in denominator is basically just works as a normalization factor of the numerator. So this evidence can be computed by integrating this numerator over the all possible source parameter values theta. Because this evidence value doesn't depend on theta, so if our goal is just to infer the source parameter values theta, then we don't need to calculate this evidence value. But if we have a multiple signal hypothesis and our goal is to compare them, then evidence is a very powerful tool. For example, if we have two different hypotheses, M1 and M2, that can be, for example, a noise and a signal hypothesis, or that can be a different gravitational waveform models. And if we want to compare, if we want to test which hypothesis is preferred by data, then we can just compare evidence values for those hypotheses and compare their values. So this is a so this provides a very simple and powerful way to compare those hypotheses. Okay, finally, I will also explain how the likelihood is obtained. So this is a bit complicated, so I will use a few slides to explain how this is computed. So first, to determine the functional form of this likelihood, we assume that we model the data as sum of the CBC signal H and instrumental noise N. And under this data hypothesis, we can move the signal CBC signal from the right-hand side to left side, and we can equate data minus CBC waveform to the instrumental noise N. So under this model, we can prove that the likelihood function is equal to the probability of obtaining data minus CBC waveform under the noise hypothesis. So once we specify the statistical properties of noise, then we can compute this likelihood. And in CBC parameter estimation, we typically make these two assumptions for instrumental noise. The first assumption is that the instrumental noise is weakly stationary. That means the expectation value of noise is constant and doesn't depend on time, and that a correlation of noise values at two different time values depend only on the time difference between them. And under these two simple assumptions, we can show that the Fourier transform of the instrumental noise is vanishing for non-zero frequency points. And more importantly, we can prove that the correlation of different frequency components is approximately diagonalized. So this correlation is proportional to the Kronecker delta. Here, this S over F is defined by this and referred to as the power spectral density, or PSD for short. And this quantity basically characterizes the noise variance at a certain frequency point F. So the higher PSD value means that we have a more instrumental noise at that frequency. I will briefly explain how this PSD is estimated for parameter estimation. And the second assumption is that instrumental noise follows Gaussian distribution. This is a simple assumption. And combining those two assumptions, we can prove that the instrumental noise follows the Fourier transform of instrumental noise follows this simple Gaussian distribution with the diagonalized covariance matrix, as you can see this. And this this noise distribution model is referred to as Whittle likelihood. Finally, substituting the data minus CBC waveform model into the noise, we obtain the standard stationary Gaussian likelihood for CBC parameter estimation. Observing this functional form, we can notice that this higher value of this likelihood means that smaller norm value of data minus waveform. So this likelihood function is basically an indicator on how well the CBC waveform matches the data. So that makes sense. Okay, so we know how to obtain likelihood. I will briefly explain how the PSD is estimated for CBC parameter estimation, because it is also a required component for likelihood. Because PSD is defined is basically a noise variance multiplied by some factor. So one of the simplest ways to estimate this is to collect a lot of tens or hundreds of data sets around the event, and calculate the average of their variances. So the right figure shows a PSD estimated in that way around the GW15 and 14. While this is a very simple and quick way to estimate the PSD, there is one concern that this PSD requires data over a very long time, and the noise variance actually, and during that long time, noise variance can evolve. So, so there is some concern about the noise stationarity. This is basically a noise stationary issue. And to mitigate the biases from the this non-stationarity of noise, there is another approach that directly fit the spectra of the data around at the time of the event. And this second approach is
we are located in the interior of this vessel. We can safely freelance. Okay. So, what we for parameter and how we compute probability density function. Okay. So now we can compute the probability density function. That Bayesian posterior probability density function is probability density of many parameters. At least 15 parameters, as I explained in the previous slide. So it is still difficult to extract the information, astrophysical information from that high dimensional probability function. So what we need to do is to integrate this probability density function over the parameters with respect to parameters which we are not interested in to obtain the
four-dimensional probability distribution of parameter we are interested in. So for example, if we are interested in the secondary mass, then we can we integrate probability distribution
over the parameter for secondary mass to obtain this one-dimensional probability distribution. Or if we are interested in the source direction, then we integrate probability density function over the parameters except for right transition direction. Oh, by the way, these
integration steps are often referred to as marginalization, and so I'm going to use the terminology. And those lower dimensional probability density function are often called marginal posterior distribution. While we can obtain this, and you can see that to achieve this marginalization, to do this marginalization, we need to. You can see that we need to do a very high dimensional integration, and doing this integration numerically with conventional grid-based approach, it should be very computationally costly, and practically, in many cases, practically not doable. So we needed to consider develop a method to think about a method to do this marginalization. So in CBC analysis, what we typically do is to use the take the Monte Carlo approach and generate the random samples following the Bayesian posterior distribution and histogram them.
So the idea is,
okay. So if we are
only interested in, for example, if you are interested in the secondary mass, then and if we can efficiently generate the random samples following the posterior distribution. Oh, by the way, random samples following the posterior distribution is often referred to as posterior samples. So I'm going to use that terminology. So if we can efficiently generate posterior samples, and if we want to know the secondary mass of the CBC, then what we do is to just read in the secondary mass values from the posterior samples and histogram them, and that will very easily produce the one-dimensional probability distribution of the secondary mass. And with that method, we can easily generate the one-dimensional or two-dimensional marginal distribution of whatever parameters you are interested in. So this Monte Carlo approach still requires an efficient algorithm to generate posterior samples, but fortunately, we already have several efficient algorithms to generate posterior samples, such as the Markov chain Monte Carlo method, or MCMC for short, or nested sampling techniques. So we use one of these techniques for CBC parameter estimation. Okay. I cannot explain the details of those stochastic sampling methods here, but to give a sense on how those methods work, I will
just demonstrate one of the very simple MCMC algorithm, which is referred to as Metropolis Hastings algorithm. And I will demonstrate that for this two-dimensional simple Gaussian distribution. So these contours represent the constant probability lines of the Gaussian distribution, and the Gaussian peak is located here. So this Metropolis Hastings algorithm first start with a random point drawn in this parameter space. So here this is an initial point, and then next we propose a next point, which is denoted by theta prime, with a certain proposal distribution function, which is denoted by Q. And important point here is that we don't always accept this jump proposal, this proposal, but sorry, can I? Okay, sorry. So we don't accept this jump proposal. We don't always accept this jump proposal, but we accept this jump proposal randomly with this probability. So sometimes this point jumps to the next proposed point, and sometimes this point just stays at the current position. And as you can see, this probability is proportional to the ratio of the posterior value at the next value at the next point and the current point. So you can see that the jump proposal to the point whose posterior probability value is higher is likely to be accepted. So if you repeat this proposal and acceptance, then this move is likely to move toward the peak of the Gaussian distribution and stochastically explore around the peak. And it can be mathematically shown that this point is going to converge to random samples following the target posterior distribution. So this movie shows 1,000 random samples following this proposal and acceptance steps. And you can see that those points converge to the samples following this two-dimensional Gaussian distribution in this two-dimensional plot, and the top one-dimensional plots on the top and the right. So I just note that this is just one of the simple example algorithms, but more or less the many sampling stochastic sampling techniques basically start with randomly drawn samples in the parameter space and let them stochastically explore so that they converge to the posterior samples. So and so we don't and actually we don't need to we already have a various open source surplus developed by people. So we don't need to actually write codes to do this MCMC, but from the scratch. But we can just install one of them and apply it to your problem in many cases. So there are many MC samplers such as EMCE, PTEMCE, and so on. And we have many nested samplers for nested sampling, such as the dynasty and nested and so on. So we can use them also for CBC parameter estimation. Okay, so now we learned how to compute the Bayesian posterior distribution and how to draw the posterior samples. So combine them, we can do a real parameter estimation analysis. So to do that, I would like to introduce I would like to introduce very useful open source parameter estimation libraries, which is named Bilby. And this Bilby is actually one of the softwares we use for the collaboration parameter estimation analysis. So this Bilby library is written in Python, and can be easily installed with pip and conda. And pip, the BLB has all the necessary components for CBC parameter estimation, such as the CBC, stationary Gaussian likelihood, frequently used CBC priors, and useful CBC parameter conversion functions, and so on. So utilizing this, you can easily start the CBC parameter estimation. And this BLB supports many of the open source samplers, which I introduced in the previous slide. And BLB also has one built-in sampler named BLB MCMC. So you can use one of them to do your parameter estimation. And so, BLB is actually written applicable for general problems. So in addition to the real CBC signals, you can apply it for the general non-CBC problems. And it can be also used to simulate CBC signals and analyze them. And you will learn how to do it with BLB through the tutorial after the lunch break. Okay, so that's it for the background, and you will learn a lot of things in the tutorial. In the final few slides, I would like to briefly introduce how you can deal with the posterior samples produced by parameter estimation analysis. So firstly, I would like to let you know that for simple study, you don't even need to do parameter estimation, but you can just download the publicly available posterior samples produced by the collaboration. So the posterior samples for CBC signals detected during the previous observing runs are available through this link. And once you install one of the posterior samples from these links and see the content of them, of it, then you will find that the posterior samples has this kind of spreadsheet-like structure. So the each row represents each source parameter, and each column. Each column represents each source parameter, and each row represents the values of each sample. And if you are interested in one of the parameters, then you just need to read in one of the columns and just histogram them, and you can very easily generate the one-dimensional marginal posterior distribution. So as you can see, as you see in this left figure. If you also want to compute the 90% credible interval, which is basically the interval whose total probability value is 90%, then you can just sort those samples and just take the 55th and the 95th percentiles of the sample, and then you will get the lower and upper bounds of the 90% credible interval. Or if we are interested in the two-dimensional marginal distribution, then again, you can just read in two columns, or two of the columns, then and make the two-dimensional histogram like this. And this two-dimensional histogram is very useful to understand the correlation of different parameters. And if we want to know more about reading and plotting samples, then you should go through the tutorial after the lunch break. Okay, this is a summary. So as I explained, we can measure the source parameters such as masses, spins, and tidal deformability parameters of colliding objects with observed gravitational wave morphology. And we typically use and what we do is to compute the probability density function of those source parameters. And we typically use the Bayesian framework where the Bayesian posterior distribution is computed through the Bayes theorem, and likelihood part is computed under the assumption the stationary Gaussian instrumental noise. Because the obtained Bayesian posterior distribution is a distribution of high dimension, so we need to do a marginalization, and we typically use a stochastic sampling method where we generate thousands of posterior samples and make their histogram to obtain the one-dimensional or two-dimensional marginal likelihood. Okay, so that's basically basic. And if you are interested in more details about it, then you can also check those references. Okay, so that's it. Thank you.
Thank you very much for the nice talk. Any questions for on-site people? Yes, please.
I have two questions. The first one is you mentioned the binary black hole merger and the binary neutron star merger. And those parameters we would like to search. So how about the BHNS sample? Because there is only one neutron star, so should we also consider the tidal deformability of the only existing neutron star?
Yes, we can consider tidal deformability. So if the mass ratio, the masses are, how to say, masses are very different, then because the neutron star is a secondary one, so that its tidal effect is pretty negligible for that case. But if the masses are comparable, then that tidal effect can be a significant can significantly affect the morphology and can be could be measured with the CBC signal. So it depends on the mass ratio.
Okay, the second question is about the constraint of the wire. In my personal search, because I have no idea about how to set the prior, so maybe I just search some papers and to get some basic information about the non-gravitational wave event. But for the real measurement or real search on site, we don't have any information of a new event. So how can we set the prior in the parameter estimation?
Yeah, that's a good question. So in the standard CBC parameter estimation, we typically use uninformative prior. So for example, we use a uniform distribution in masses and a uniform in spin magnitude and isotropic spin direction. So for such a new events, we try to use as uninformative prior as possible.
Thank you.
All right, let me read one question from online. So is BLB specifically used in GW research, or can it be used in other research fields which also involve similar type of parameter estimations from the observed data, such as 21 CM cosmology?
So I'm not sure about that specific cosmology issue, but problem. But yes, BLB can be used for basically general inference issue. Like for example, for example, it can be used for fitting the points with a linear function, or it can be used for for analyzing the other burst signal other than the CBC. And I think one of the tutorials covers that point, I think.
Okay, thank you very much. Oh, yes, please.
I have a question about parameter estimation. While we doing a parameter estimation, is there any different using the maze 1, maze 2, and the travel maze and the maze ratio?
Oh, yeah, that's a good question. So I don't have. So, okay. Maybe this is useful. Well, it's a bit, okay. Yeah. So the issue is that, as you can see in this plot, the two mass values are correlated, as you can see, because, what we precisely measure is Chirp mass. So this distribution roughly follows the constant line of Chirp mass. So actually, this is a short signal, a relatively short signal. So it's not very correlated very much, but for neutron star case, it's basically a single distribution is basically a single line along the constant Chirp mass line. So in such a cases, the problem is that you need to, stochastically explore the along that Chapman line, right? And and without knowing that correlation, sampler stochastic explanation can be very inefficient because it's very less likely to hit the peak of the posterior distribution. So actually doing sampling with respect to component masses is very inefficient. And what we do is to do parameter transformation to sample over chirp mass and mass ratio, because in that case, the distribution should be very uncorrelated. Well, there is still correlation, but less correlated. So, and then stochastic explanation can be more efficient.
Okay, so if we want to check the each want to check the correlation of two masses, we should use mass 1 and mass 2. If we want to enhance our efficiency, maybe we should choose true mass. Is that right?
Yeah, for efficiency, we should choose chirp mass and mass ratio. Oh, and it doesn't change the results actually, because we properly take into account the Jacobian of the transformation. So as long as we take into account that Jacobian, then the results should be same.
Oh, okay, thank you.
Yeah.
All right, let me take one question from online here. So how does the precision would affect the ring down phase? And in the case of BHNS merger, how would the change in the signature of tidal disruption will affect the ring down phase?
Ring down phase.
Yeah.
Okay, I think that I already just first try to take the first question.
Yeah.
So yes, yeah, yes. So the ring down actually affects the CBC parameter expansion of high masses, right? So what we can measure is like for high mass events, that the ring down part can be in the will be in the sensitive band of the detector, and we can especially we can measure the frequency of the dominant ring down mode. So by measuring that dominant frequency of that dominant ring down mode, we can infer some combination of the remnant mass and spin, and using that information, actually we can measure break the degeneracy between masses and spins, and we can more precisely measure each of the parameters. So that affects the parameter estimation. I'm not sure about the impact of the tidal disruption on the ring down, but yeah, for comparable.
So maybe I misunderstand the question. Actually, the question should be the changes of the BHNS waveform when there's a tidal disruption change. I think that should be the question. Yeah.
Yes, that changes. So for comparable mass, so for I should say comparable the NSBH is comparable masses, then tidal disruption can happen before the merger, and that affects the waveform.
Okay. Okay, maybe another question from online. So how well does the Gaussian noise ansatz fit the different noise sources for LVK detectors?
So is it the question about the Gaussianity of the noise, or question about the?
I think the question should be how well does our data in LVK fits the Gaussian noise? So yeah, and there's a further question asking if there's any reference where we can find the significance levels for the Gaussian posterior of the strand noise has been quantified as a function. Yeah, I think the question should be how well does our data in the detectors close to the Gaussian noise?
Yeah, so that's good question. So in reality, we have transient noises in gravitational wave data, and that makes your noise distribution not non-Gaussian. We also have a non-stationarity of the noise, and you know, that can also broaden or shrink your distribution. And well, so we try to mitigate that non-Gaussian effects before doing CBC parameter estimation. For example, if we identify notable glitch noise overlapping the CBC signal, then we use a so-called Bayes Way algorithm to subtract it. And we also, as I said, we also use on-source spectral fit methods to estimate the PSD to mitigate the non-stationary effects. And so we do some, before doing CBC parameter estimation, we do those kind of analysis to mitigate that effect.
Okay, thank you. All right, then another online question. So why cannot we just use the parameters of the template when we do the CPC match filtering search? Why can we not just use those parameters which has the which passes the chi-square test?
Okay, yeah, that's also a good question. That is basically, okay, I think that there are two problems, I think. First is that, that is just a point estimate, but we have a measurement errors of the mass and spin values. For example, you can see that the, distribution is just doesn't, is not a Gaussian like a small Gaussian center that's one point value, but it's a broad. So we need to do detailed CBC parameter estimation to understand the uncertainty, measurement errors of the noise parameters. So that's one thing. Another thing is that because to reduce the computational cost of the search, we just consider a very simple waveform model where the spins are just in parallel with the orbital angular momentum. But in CBC parameter estimation, we take into account more physical effects, such as the case where spins are not aligned with the orbital angular momentum, and there can be some orbital precession effects of the orbital orbital plane. So those kind of those more complicated physical effects are also took into account in the parameter estimation.
Okay. Any on-site question? No? Then we can take another online question. Let me see. So can you suggest any reference or materials on the derivation of the chirp masses, spin parameters, and the tidal deformability parameter?
Okay, yeah. And for chirp mass, you can just read one of the textbooks of the gravitational waves, such as there's a nice textbook from Majore, or a nice book about the Jory and Crichton and Warren Anderson. For spins and the tidal deformability, yeah, I don't remember the author names for that, but there are some papers, especially for tidal effects. Yeah, there is one paper that proposes that we can measure the tidal deformability parameters with with design sensitivity of LIGO. And sorry, I cannot point it in the now, but maybe later I can contact that person offline.
Yes, yes. Maybe you can just throw the links in the chat here.
Yeah.
Okay. Okay. Any on-site question? If no, there's another online question here. So would you please go to your slide 2? I think that should be, the template here. So what's the shortcut of the straight line here? What does that mean?
I think this one, right?
Yes,
Ah.
that's right.
Because M1 is larger by definition larger than M2. So this is just a line where M1 is equal to M2, and we only need to consider this lower light vision.
Okay. All right, any more questions? I don't see any new questions in the chat or Q&A. Okay. If so, I think we can conclude this session. Thank you, Morisaki-san.
Thank you.